All right, so we're live for today's session. And I feel like me versus Cuda is like tragically failing. I need a better plan of action um, than I had yesterday. But if you're new to the stream, I'm Christina, data scientist, learning some deep learning stuff, just holding myself accountable by showing up and making myself stream on the internet for an hour a day for the next 28 days as I go through different topics that I need a refresher on. This week, we actually don't need a refresher on Cuda. I've never learned Cuda. I guess it's like C++, GPU programming. Um, yeah, so we started the week out with reviewing videos, talks, lectures, going through other people's study process, and now kind of need to find a slightly better way to go through it all. Um, because the way I'm doing it right now isn't making it happen. So I'm thinking I found a different video series that's based on the book Everyone Thinks We Should Get, but I can't get the book right now. So um, how do we get to learn? This YouTube channel seems to have a lot of videos, and I hate learning through videos because I don't learn through videos. And I like people explaining it and me making notes and on in a book. So, but you can't have everything, right? Um, so I think we left off yesterday. I was trying to. I can't code at this time of day, unfortunately, but it's the only time of day I can stream. It's like my brain just doesn't compute logical structures, and I'm very rusty because I haven't had to work in like C++ in a very long time. So we have this notebook, which is the original notebook given to us to learn this block of code on. And I guess maybe what we can do is just keep going line by line and try to figure out what it does. Or I can start the lecture series and watch the streaming of the videos. I don't know. I never make these decisions before I go on live either. Like time. And this notebook we've been working off of is the first little section here. I guess maybe since I am struggling with compute and memory architecture, I might just need to watch the video on compute and memory architecture and see if it helps with the visualization of it. Because I'm not like sure why we're doing all this math. I get that we're making a grid of items and this is the tensor, that would be the tensor when we were checking it, but how does this translate and like why do we do it this way? And I get that he puts his code into ChatGPT, which I guess works, but I like to understand a bit more. Like he uses ChatGPT to translate his code from Python to Cuda. And I'm not trying to do it that way. So okay, let's go ahead and watch on Intro to Compute and Memory.
Web.com's AI.
Go ahead and open a new tab.
Hello and welcome to today's session of our Cuda mode reading group. We're reading the Programming Massively Parallel Processors book, and today we're reviewing chapters 4 and 5 in the material. So what's covered there is the compute and memory basics. Remember that we want to go fast on the GPUs, and that for that we have to kind of dive a bit into how they're doing. I'm Tom Wieman. I'm with Lernapparat, the blog, and I run my own small consulting company, but actually next week I'm starting at Lighting AI. My good friends there. Okay, so the first thing to look at is the compute architecture and the scheduling. We saw that you had like threads and blocks in the last 2 sessions already, and you know that by now. But how does that relate to how things actually run on the GPU? And what do we have to know to keep the GPU busy? So the first thing here is that in contrast to the CPU, where you have like lots of things in the CPU core, fetch decoder unit and all that, and then there's an arithmetic logic unit, a single one per core, or more or less a single one. In contrast to that, on the right, you see the streaming multiprocessor, or actually this is about 1/4 of it, a compute unit or a computational unit in here. It has many arithmetic logical units, and it has some bit of context for each of them, but there's a lot of shared context. And so each of these will run one thread, and so this will be the thread information, but then there will be a lot of shared information, and in particular, fetching and decoding the commands will be jointly for a group of threads. Originally, this shared part included the program counter as well that tells the GPU like what's next to compute. Now each has one, and this is one of the sources where the book is a bit outdated if you have the more recent GPUs, Volta and following as a model. Okay, so this is how the book pictures the GPU with its multiple streaming multiprocessors. If we look at a real GPU from today, so my GPU is a RTX 3090, or one of them. This has 82 streaming multiprocessors. You see them on here. And all these are more or less independent, the streaming multiprocessors, but we have lots of them. They share one common L2 cache, that's here in the middle. And one thing that the consumer or non-data center GPUs don't have are floating point 64 cores. I've left this note in here that the FP64 rate is 1/64 of the FP2 T-flop rate. And this is because it just doesn't, it has 2 compute units for 64-bit floating points just to make the programs run at all, but they're not going to be fast. And of course, Andreas noticed this when you use 64-bit floats as constants per accident, then some of your computation will be in the 64-bit regime, and this will be slow. Okay, so let's look at one of those 82 streaming multiprocessors. It's pictured here, and I took this from the white paper that I'm linking in the last slide. It looks like this. It has 4 units, if you want, so 4 parts here. And each of these parts has its own register file and its own scheduling and dispatch unit for 32 threads per clock. And then it has the compute units, and you see that it has 32 FP32 units, and half of them can do int32, actually. And then it has the tensor core units, but we're not going to look at that today in great detail. So when you run a kernel, you define the block and how many threads are in a block, and you define the grid layout, how many blocks there are. And so each thread block is assigned to one of these streaming multiprocessors, one of the 82. And so we don't have any control which block will go where. In the most recent GPUs, you can have thread block groups, but we'll leave that for now. And so you have no control which block goes where. And each of these streaming multiprocessors can process a number of threads that is higher than the maximal number of threads in the block. That means that several blocks can be assigned to the same streaming multiprocessor at once if all the other resource limits are kept under control. So, for example, for the RTX 3090, you have a maximum of 1536 threads assignable to the streaming multiprocessor. So ideally, our block size would divide this number. So a block size of 256 or 512 is probably better than a block size of 1024 threads. If we want to make sure that there's as many threads waiting to be executed on this streaming multiprocessor. So each of these can process one warp, 32 threads at a given time. Sometimes the warps will diverge.
Hold on, I want to see.
Tired of waiting months to get the team you need? Build a flexible workforce with Upwork. Upwork gives us access to
print.
I don't think it's going to go over what I want it to go over. Let me see. Let me check out the slide notes first, maybe. Oh no, this is the one he's doing now. Okay, so now I think it keeps going.
If we do it,
I'm stuck somewhere else. Okay. Then I guess the best thing to do in this case is dual screen what we need to look at and see if I can't understand what's happening. So this is the Cuda setup, and this is the Python kernel. Okay, so yeah, this is how they change it from RGB gray. So this is just creating this same kernel in Cuda. All right, so here is Python. You don't have to do anything. Here you have to tell the type of variable. In Python, it auto creates the grid maybe. Or we create it somewhere else. Because we don't see it, we don't here we are defining the grid first. So yeah, and this is the grid that it creates, and this must just be the standard math for that. Okay, RGB to grayscale. Now we're looking at this to this. So check input. Check input is a built-in function. Okay, so let's see. A built-in method, I guess. Check input. Okay. This looks like it's a custom extension. It tells why we use it. It doesn't, but let's go back and see if we can't find the original documentation page. I'm craning my neck even though this is a big TV in front of me. Check input. Cuda. Okay, well, to look there. Guess I don't get to know exactly what it does or when I get to call it. I'm looking at it checks input of something from the title. That's all I got. So once we do that, just like we do here, we give it the shape. Here we're giving it the shape of the input X. Here we're just saying input.size1, input.size2. Here it passes the input. Okay, so if we why the size 1 and size 2 if that's just the shape of X? Well, what happens when you put shape into 3 variables? So let's see. Does it have any special attributes that I don't use it for normally? This is the question. Actually, why am I on DistroOcean? Where's the let's check what packages were imported. So this is .shape from NumPy, or so many packages have shape. So let's look at NumPy shape first. It's a tuple of array dimensions. Okay. Or tuple, I don't know which one it is. So if this is NumPy, this gives the first thing here that was in this tuple and the second one. And according to this, there are 3 different tuples. So if I run grayscale image, it gives the 3 different dimensions to here. Here I only give the dimensions here. This doesn't seem to define the dimension C. Okay, well if it doesn't do that, N is H times W, which is here. Torch empty input options. That's this. And if I had input options, so I have a few things I don't know what it is doing. This is running the kernel. And this initiates the grid of this size and threads, which is defined here. This is PyTorch. Guessing it's this. And the stuff that is in here. And if I'm running kernel, this as well. It returns an output. Okay. It's just, some things are lost definitely in translation. Like here we have to flatten, but I don't see any flattening here. Does that mean that it auto flattens in Cuda? Or it's not a requirement? This is okay. So let's go back. Okay, so this is more of a direct. Here to here, when it creates a block. still have the flattened the C here. And I wonder if check input is the equivalent of C, or when you have this shape. So then you only define 0.1 and 2 maybe. Flatten, I don't know what flatten does. But you also don't know you do define threads. So it creates the blocks. H times dB divided by threads. Here it doesn't seem to matter. Okay. So let's keep Python here. Okay, and look at Cuda. This is it's broad class name. Doesn't make much sense translated over. Okay. So I guess once you define your block of the math required in that block, it's really this torch tensor input that we have, which is PyTorch's Cuda extension. That doesn't make all the sense in the world. Okay. Where's the extension library? Cuda semantics. I guess it doesn't matter if you run it natively in Torch using just the built-in extensions. Let's do this. See if it'll generate language. Okay, this is the C++ front end. So now we're cooking with some grease. All right, Torch tensor in this format. So basically this week. So we start the kernel in the Cuda construct with whatever grid or whatever threads math needs to happen. And then we move into PyTorch C++ front end, which is this part of the code, which we have these components we can use. This specifically is tensor. And so here, because it's the PyTorch C++ API, I'm just going to start this. And Cuda and C++ documentation to get the one I want. Actually, let's go with the first one and work our way down. Class tensor. Okay. Types. This is, this class tensor, tensor name, open parentheses. How do you keep C++ documentation to understand how to use it? More difficult questions than answers. All right, let's start. Okay. With the top, I guess. No. Void check input. We don't have a void, but there's no other input on what this is. Oh, this is for the recurrent clonable base. I guess they must have a check input for tensors. Okay, let's look at these class names. We're not in any neural network. So none of these are what I would want for this one. Let's go back one more. Go for one and type in. Okay, class tensor. And let's go to class documentation. None of that makes any sense to me. Like there's no thing to click on and get any more information. And I wonder if people think this documentation is good. Like when I look at like Pandas documentation, I get examples, I get explanations of all of the variable types. Like, I guess this means you need to put in some time to help get this better documented because, which I don't understand C++. None of those make sense. I'm not trying to do any of that. No add ReLU classes. None of that. So, well, we know this is the class tensor. And it's taking another class tensor in the input. But why? Here, they do it here too. So I guess we can just take it as standard, but and the name of this function is forward. And it takes x. But here, we call this class tensor so much, and I'm not actually sure why we're doing that. We call it, and then we assign output equals another empty torch tensor, which I get that that's like empty tensor. Always tired. I might have to buckle and get the book and try this again next month. Because I'm not sure why you would do that twice. Like, use the same word after you're in the class already. Like, why double say it? Because, let me see. Like here they don't. But I get that this is making a neural network. It's the same like dropout ReLU softmax. That makes sense in context. I wonder if this is just this is just getting the okay. So tensor creation API. How I got there, I have no idea. So we create a torch function name. And function receives options. Sizes tensor options. So we're invoking tensor. Let's bookmark this page. All right. Are any required or optional parameters? No, they didn't put any tempo. The size of the type of instance of attention. Okay. So then once we do that, we have empty, which is this one. Returns a tensor with uninitialized value, so it's just an empty tensor. Got it. Here is feel like, are we creating another? What is it? Did we call it? Name the function we like it. It's like it's invoking tensor again here. Create some specific size tensor values. Layout device. So yeah, this is what I mean by detailed information of what's happening. Okay. So torch tensor options, which we didn't need options because I don't see here any auto options. Okay. It does call dot options. I wonder if that's the same thing or if they're calling that from the actual like PyTorch option. And would this be a better way to do it? So let's check. See if it takes me there. So it is invoking the options. But it feels like it's pulling from two different things if this is how they're doing it. I'm losing my spot. Okay. So theoretically, I guess you could do this or you could do this. Torch options. Why is it input dot options? Let's see. It's it doesn't do any options here. Okay. See what else we have. Tensor basics. This is reiterating how to access it the Cuda way. Okay, so I kind of get this now. Calling different classes that invoke the PyTorch same version with the C++ front-end API extension mixed with some regular PyTorch because those don't seem to be the format for the C++ extension. we didn't turn on any inference mode. No auto grade, but I'm guessing we can do that if we want. Dollar still, we can do that if we want. I'm just checking through. It's equivalent. Okay, so I'm fine. I get this now. Okay, so I think I'm gonna spend, now that I get kind of what this is and what it means, like class name, function that we're trying to invoke, input we're passing, function we're trying to invoke, input we're passing. Now, we check both inputs coming in, we give it our sizes. This torch check, I don't know where that comes from. Did we make torch check somewhere? Guess it's built in. Wonder if I search if I find it. There we go. Doesn't tell me what it does. Okay. This is that auto output that we saw earlier. Okay. So it switches back and forth between the PyTorch code and then the C++ front end code. And that's why we see the mix of like syntax here. That was confusing for me. So that solves this problem. I guess that does mean that now I should be able to write the code in PyTorch and then translate that code into Cuda. I think those are going to be my steps. So let's get a text. So one, after I input format data. That's going to take a few hours. Format data to write in PyTorch and then translate to C++ front end API PyTorch. It's okay to mix PyTorch Python with C++ front end and code, at least for now. We can check the optimization on that after we get that much done. Now that I understand what it's doing, that leaves me with trying to split my data into train test sets. I think yesterday I got sidetracked here in the sample data. But thankfully it doesn't persist. So if it doesn't persist, I can re-download it from the URL. So this will download it and unzip, and then I can move it. If I wanted it to persist, I'd have to do that Google Drive attachment to the notebook, which is the better way to do it, but we're not doing it that way right now. And we only have 10 minutes till 7, and I still need to eat dinner. Okay, let's write what needs to happen. This is going to, once it's downloaded, say what to see if this works. Refresh. Yep. Okay. So now we're just going to do that for the other folders. Okay, so refresh. Not what I wanted. This. Actually, let's try this. No, that would be dumb. Let's just finish reading documentation, the angst of my existence. I don't think that's going to help. Let's try it. No, it won't help. Okay, let's just do the glue thing. death of me is. Okay. I think running it all together is going to do a darn thing. No, didn't do it. Okay. Funny how things don't work the way you want them to work. Okay, I will stop trying to do it the easy way, and I will just have to iterate over each folder, each subdirectory, and randomly choose from each subdirectory, since I can't move anything. Because I want to. Well, actually, it's going to go for validations. Then it's tested out something from the internet. Okay. Don't need this. Or this or this. Okay, so it's 7. I guess tomorrow. Now that I get how that code was written, kind of. We'll start here. I don't need this or that. But we will need an import at the top. Okay, so I guess we're ready for tomorrow then. All right, I'll see you guys tomorrow. You can keep at it if you have time. But yeah, this is kind of what we want to do. And this is just for kicks. 80-20 doesn't have to be that way. I want to do 60-40. For kicks. All right, I will see you guys tomorrow.